Class C works well because the transistor is on for only a tiny bit of the time, but it's still dissipating power while it's varying its voltage while it's on. The next step up would be to say, let's replace those outer transistors with a switch. If we did that, so instead of having a transistor operating in a linear form, when we start needing more voltage on the output of our amplifier, we literally switch in a higher power supply voltage, thus boosting the ability of the transistor to output high voltages. Again, that's only going to happen to that transistor for very short periods of time, so the efficiency goes up. The real advantage of this is your switches are actually a lot smaller, dissipate virtually no power at all because they're basically on or off, so they're either no current or high voltage across them, which is low power, low power dissipation, or they're high current but with no voltage across them or minimal voltage across them, again, low power dissipation. So you never operate the outer transistors in a mode that causes them to have to dissipate a lot of power. You get slightly better efficiency. Switching them on and off in time to the signal is the tricky bit, because obviously if you're late for the party switching things on, it's not going to sound good. And switching them off in time afterwards is very difficult. A 20 kilohertz signal does move quite quickly if it's a high voltage output. So timing can be a bit tricky, but in effect what you're doing is modulating the power supply, but in a stepped fashion using the switches.
We introduced to the client this idea that you might want to equalize your system to optimize its performance. This is a revelation. Absolute revelation. These projects are under such time and budget constraints now. If you say to them, I'd like one night, please, to just go and EQ this, they'll say no. No funds for that. We had to fight over a period of weeks to say, look, this is what the modelling shows. We can improve things by applying equalisation to the voice alarm scenario. It gives us a better or status quo STI, but we get a lower overall level. So what we're looking at here, well, we've got these SPLs on without EQ, and we can reduce those and achieve the same result. And it may not feel like much, but that's a major win to lose 3 dB on the platforms outside when the residence window is here. Okay. Also, it does help it sound a bit nicer. Bearing in mind, they've got these people going around saying, does that sound nice? Oh, yeah, I think it does. So they took that on board and said, yeah, okay, we will allow you time to do that. And so from that point on, the equalisation, having been established for the voice alarm, was then carried over to all the PA scenarios because it was going to be in and it was fixed. We studied 18 designs for just loudspeakers alone. And they were all compared against a control scenario, which is here. Now, operationally, we have a ticket hall, the inside shed platforms, and then the canopy platforms in the cut. They do run those all as one zone. Effectively, we'll announce PA across that because they're dealing with one particular tube line. They will talk about it. There's a walkway up here at higher level, which we'd already convinced them in 2000 shouldn't do PA, and it still doesn't, and it doesn't in the control model either. So what you can see is all these lovely loudspeakers and this lovely smooth coverage. We've got an SPL approaching 87 to 90 dB.
I have chosen a limited number of technologies, and there's a reason why the talk is called network audio and not digital audio. And the first one, why these protocols have been chosen to be investigated are because they all support uncompressed signal. I consider all of us working in the professional audio, we don't do compressed signal. YouTube does compressed signal. That's good for them, but not for this. They have to allow full bandwidth, full uncompressed digital audio. The other one is that they must do low latency. One of the huge advantages of analog audio is that it suffers from almost no latency at all. As soon as you start jumping into digital, latency does become a big problem. In professional audio, latency is just not acceptable beyond certain limits. So everything that we're going to be talking today, they all support low latency. And the last qualifying criteria to be included in today's talk is that they must allow interoperability between different manufacturers. There are network digital protocols out there, but they belong to one manufacturer, and for very valid reasons of their own, they don't allow other manufacturers to implement it. As such, I have removed them from this talk because they are very brand specific. All of the ones that we included here, for one means or another, any manufacturer is able to go, pay the license, or download the implementation papers, and they can include it in their products. Make sense? Now, network audio suffers from one major problem, and that is that Ethernet networks were not designed to send audio. Ethernet networks were designed to send email, data. They don't care the order in which the packets arrive. They don't care about the latency in which the packets arrive. They just care that the packets do arrive. In audio, we really much care the order in which they arrive. We very much care about the timing, the latency they arrive. And if some of them got dropped, I don't want to listen to that speech again. I'd rather drop them. So that's a different change. And that is what people call deterministic, because what is available in normal Ethernet networks is really not necessarily a good thing for us. And indeed, when we are using most of the Ethernet-based technologies, the order by which the data arrives to us, it doesn't matter. Because when we're trying to watch a YouTube video, we are happy to wait for the spinning wheel to buffer all the data until all the packets arrive, and then they get displayed in the right order. In real-time audio, that's not acceptable. So all of the different protocols have to find ways to achieve that deterministic delivery. The first thing they need to do that is to agree on synchronization. And that is because in a network, you are going to have different nodes with different clocks. And it doesn't matter what manufacturers tell you, and I represent a manufacturer, clocks will go adrift. There's no two clocks which are precisely the same throughout all the time. They will end up being at different times. And when you're reading data, that timestamp is critical. Because if I think I'm in one time here, and I send audio to the other guy that's in a different time, he's going to be reading something completely different. And that's what distortion and jitter comes into the equation. So you must make sure that all of the nodes in a network, they are synchronized as precisely as you possibly can.